Hello everyone and welcome to my first ever YouTube video. My name's John Lunn, aka Jonnychipz, and today I'm going to be speaking to you a little bit around networking fundamentals, so really getting back to the basics of networking and really try and understand how you can take that knowledge and move into the world of Azure. Before we kick off, just a little bit about myself. So I've been working in the IT industry for coming up to the 20-year mark. I find myself over the last 8 or 9 years really working in that cloud architecture and consultancy space, helping great customers do some fantastic things with Azure. So let's move on, let's get stuck in. Okay, so when it comes to networking fundamentals, moving to the cloud and taking on a role as an Azure developer, a solution architect or an administrator requires knowing the foundations for really how networking works and how to use the different devices to build networks. So whilst networks are made up of various network devices, there are other aspects to keep in mind as well. So for example, network communications protocols require devices to have network addresses assigned. You'll also need to secure your network, really to protect your organization's assets and resources. So in this video, what we're going to try and explore is how networks communicate with each other, and we'll also see if we can learn about the networking protocols and standards and the difference between what is a WAN, what is a LAN. So finally, we'll have a little look and really get to know a little bit more about the transmission control protocol and the internet protocol, so TCP/IP and IP addresses and ports. So while the content of this video really applies to any network, the idea is really so that you guys can see where and how the concept applies to networks that are managed in Azure. So we'll start off. What is a network? So a network is fundamentally a collection of network-enabled devices. So it's typically made up of computers, switches, routers, printers, servers. Networks are a fundamental part of day-to-day life and exist in homes, in workplaces, in public areas. So networks allow all types of network-enabled devices to communicate with each other. So what we're going to do is we're going to look at 3 key areas to try and answer that exact question. So what is a network? So the key areas that we're going to look at are network types, network topologies, and network standards. So first off, network types. So they do vary in size, shape and usage. To make it easier to identify different network types, they're categorized into one of the following network categories. So you've got personal area networks, PANs. You've got local area networks, LANs. There's a metropolitan area network, a MAN, and a wide area network, a WAN. So we'll look at each of these in turn now and just try and understand what they are in a little bit more detail. So what is a personal area network? So a PAN provides networking needs around an individual. An example of a PAN might be that an individual's got a smartphone, smartwatch, tablet and a laptop all connected and all sharing data without the need to connect to an access point or other third-party network services. So PAN networks typically use Bluetooth to communicate because it's really a low power, short range data sharing capability. Network standards associated with a PAN are Bluetooth and IEEE 802.15. So next we'll move into a LAN. What is a local area network? So a LAN really provides networking needs around a single location. So this location might be an organization's office, a school, university, a hospital, an airport, and you get the idea. So a LAN is usually privately owned and needs authentication and authorization to access. Of the different classifications of a network, a LAN is by far probably the most commonly used. So let's move on to a metropolitan area network now. So a MAN is really, it's about providing capabilities between 2 different locations within a city or a metropolitan area to provide a single extensive network. Typically a MAN requires dedicated and secure connections between each of the joined LANs into the MAN. Very similar extent is a WAN. So a wide area network, it really provides networking capabilities between 2 different geographical locations locally or worldwide. So for example, a WAN is used to connect an organization's head office with branch offices all over the country, or it might link multiple LANs together to create one super network. I mean, as a MAN, you use virtual private networks to access or to manage the differences between the LANs. So let's look at really some of the fundamental differences between a LAN and a WAN. So as you can see there on the screen, typically speaking, a LAN is privately owned. It's contained to a single building, whereas a WAN, it really is connecting geographically dispersed sites with each other. A LAN in this day and age now, they typically operate at speeds of 10 gigabits per second or higher, whereas a WAN a little bit slower, around about the 1 gig mark. Typically speaking, a LAN can be seen as less congested as a WAN, although that's not necessarily the case depending on your LAN. And generally speaking, a LAN is administered and maintained in-house, so within your home or within your office building, whereas a WAN, it's typically managed and serviced by a third party, and therefore, has cost implications and can cost a little bit more. Okay, so next we'll look at some network topologies. So network topologies describes the physical composition of a network. So the five that we're going to look at is we're going to look at the mesh topology, we're going to look at the ring topology, the star, the tree, and the bus topologies. So let's look at each one of those in turn. You can see the diagram that we've got on the screen there, but generally speaking, a mesh topology is described either as a physical or a logical mesh. So a physical mesh in each network, a device connects to every other network device in that network. So it dramatically increases the resilience of a network, but it's got the physical overhead of connecting all the devices together. So few networks today are built as a few mesh. Most networks use partial mesh, where some machines interconnect, but others connect through one device. There is a subtle difference between a physical mesh network and a logical one. The perception is that most modern networks are mesh-based, since some can be, since each device can see and communicate with any other device on the network. So this description of a logical mesh network, and it's primarily made possible through the use of network protocols. Ring topology. So looking at a ring topology, really, if you can see on that diagram there, each network device is really connected to its neighbor to form, a ring. This former's network is more resilient than a bus topology. Breaking the cable ring can also affect the performance of the network. So if there is a break at any point in that network, traffic has got to traverse the opposite way and potentially take a little bit longer. So next, looking at the star topology, it's probably the most commonly used network topology that we use today. Each network device connects to a centralized hub or switch. Switches and hubs can be linked together to extend and build more extensive networks. So this type of topology is by far the most robust and scalable. The tree topology, it's really an evolution of the star topology, and essentially can be viewed as multiple star topologies, each connected to the backbone network. And this type of topology can be seen when connecting two physical buildings together, or geographic regions, for example. And finally, the bus topology. In the bus topology, each network device is connected to a single network cable. So even though it's the simplest type of network to implement, there are limitations to it. So the first limitation is the length of the main cable or the bus. The longer it gets, the higher the chance of the signal will drop out. This limitation constrains the physical layout of the network. So all devices have to be physically located near each other, for example, in the same room or in the same office building. So, and again, if there's a break in that particular bus cable, then the whole network is going to suffer, or it will fail because of that break. Okay, next we'll take a quick shift on to some of the networking standards, just so you've got a general idea of what we're talking about. So, first one we're going to pick up on is Ethernet. So, Ethernet is really a networking standard that's synonymous with wire-based LAN networks, and also used in MAN and WAN networks. So, Ethernet has replaced other wired LAN technologies like ArcNet and Token Ring over the years, and it's an industry standard. So whilst Ethernet is associated with wired networks, just keep in mind that it's not limited to wire, since it's used over fiber optic links as well. The Ethernet standard defines a framework for data transmission, error handling, and performance thresholds. It also describes the rules for configuring an Ethernet network and how much each element in the networks interacts with each other. So Ethernet is used in the OSI model at the data link and physical layers. It forms a basis for the IEEE 802.3 standard. This standard helped to unify network and hardware development. Ethernet is a continual evolving standard. The original version supported a data transmission rate of just under 3 megabits per second, and in recent years several iterations were released to keep up with the demand for increased speed. So today rates are extending upwards of 400 gigabits per second. Next we'll look at the fast Ethernet. Next, fast Ethernet. So fast Ethernet is controlled by the IEEE 802.3U standard, and it was really developed to support transmission speeds of up to 100 megabits per second. Faster Ethernet was also referred to as 100 base TX standard. Gigabit Ethernet 802.3AB was developed to support faster communication networks that support services like streaming multimedia and voice over IP. The 1000 base T standard runs 10 times faster than the 100 base TX standard. Gigabit Ethernet is now included in the 802.3 standards and recommended for enterprise networks. The new standard is backward compatible with 100 base T and the older 10 base T standards, but that's going back in time quite some way. 10 gigabit Ethernet is IEEE 802.3AE. So this standard is a nominal data transfer speed, as you'd imagine, of 10 gigabits per second, which is fundamentally 10 times faster than its predecessor. This speed improvement is made possible only by using fiber optics. So the standard now requires that 10 gigabit Ethernet networks use area-based routing rather than broadcasting data to all nodes. In that way, network noise and traffic are significantly reduced. And finally, some of the networking standards that we're going to look at is terabit Ethernet. So as the name would suggest, it's getting there. So currently terabit Ethernet offers data transfer speeds of between sort of 2 to 400 gigabits per second, and it's really expected that terabit Ethernet is going to offer speeds of upwards of 800 gigabits per second and really 1.6 terabits per second in the future. Okay, so that was a whirlwind tour of standards and protocols. So we'll just touch upon the Azure Virtual Network, the VNET. So it comes with several networking tools and services. So looking at the VNET, so using the Azure Virtual Network, you can build complex virtual environments that emulate the structure of the actual on-prem network that you might be looking to achieve. So you can provision and manage a cloud-based VNETs. You can also create hybrid virtual networks and integrate with your on-prem network. So when you looking to use that with things like VPN gateways. So connectivity services, when you have a low latency, high bandwidth connection between your on-prem network and your instance of the Azure VNet, you've really got two options. So like I say, you can either use a VPN, site-to-site VPN connection via an Azure VPN gateway, or we can use a dedicated connection through things like Azure Express Route. So an Express Route is a secure point-to-point service, and really to use that service, then you have to use a third-party connectivity partner to provide and host the Express Route circuits on your behalf. Okay, a quick whistle-stop tour through the 802 family. So a network can't really exist unless each of its devices has the means of communicating with another. This fact applies whether it's your organization's network or more extensive networks like the web. All networks are built on the same principles. In the section, we're going to look at the term network standards and explore the hardware that forms the backbones of any network. So, while network protocols provide a unified method for communication, network standards govern the hardware and software that uses them. So today there are hundreds of thousands of hardware suppliers, yet all of their technology seamlessly integrates with your computer or network with minimal effort. So network standards provide a framework that enables the interoperability between devices. So network standards improve the interoperability of different network-enabled devices. They can provide backward compatibility between product revisions and differing vendors. Official bodies that publish regulated standards, people like the International Telecommunication Union, the ITU, the American National Standards Institute, so that's ANSI, and the Institute of the Electrical and Electronics Engineers, that's the IEEE. So it would be impossible to build networks and really contact network-enabled devices reliably without these kind of standards that are in play for us today. So the family of standards that we're looking at there on the screen is the IO2 family of standards. So the 802 family of standards. The 802 family specification covers all the physical networking standards for both Ethernet and wireless, and on that table on the screen you can see some of the more widely used standards, and I'm sure some of those will be familiar with you. Okay, networking infrastructure. So there are several networking standard compliant devices that make up structure of networks. So dependent on your network size, you might use several of these devices to build the backbone of a network. So things like repeaters, hubs, bridges, switches, routers. Nearly all of these devices, they really depend on what we know as a media access controller, or a MAC address, or an internet protocol, an IP address, to really deliver the data on that network. So what is a media access control address, or MAC address for short? So the media access control address is a unique identifier assigned to every network-enabled device at the time of manufacture. It's sometimes referred to as the burned-in address, the Ethernet hardware address, or the physical address of the device. So the MAC address is a standard composition of 6 hexadecimal numbers separated by a colon or dash, as you can see there on the screen. The first 3 numbers of the MAC address define the manufacturer's organizationally unique identifier, their OUI, and the remaining 3 numbers uniquely identify that particular device. So, for example, if the MAC address is AA, 6A, BA, 2B, 6A, C1, and the OUI is that first 3 sets. So the OUI is the AA, 6A, BA, and then the 2B, 6A, C1 is the device ID. So we'll have a quick talk around a few of these devices now briefly, just to understand what the differences are, because there are subtle differences across some of these devices. Even though they may look very similar to each other, they may in fact be very similar in their operation. So first off, we'll talk about a repeater. So realistically speaking, a repeater is a 2-port device that repeats network signals. So repeaters are used when network devices are quite some distance from each other, and it doesn't modify or interpret any of the data packets before it resends them on. It's simply there to amplify the signal. So what it does is it just regenerates the data packet at the original strength bit by bit and sends it onto the next spot. So like I say, over long distances, repeaters are used. A bridge. So what a bridge does, it divides a network into network segments, and it can filter and forward data packets between these segments. So bridges, they're commonly used to on network devices MAC addresses to decide the data package's destination. So typically a bridge is used to improve network performance, really by reducing unnecessary network traffic on network segments. A hub, so this So a hub, it acts as a multi-port repeater on a network. So hubs are used to connect more than one device and structure the layout of a network. So for example, you can use cascade hubs to create network branches, or as an endpoint to create a star layout with multiple user type devices. Hubs contain multiple ports, and they act as input and output Ethernet connections between hubs and the network devices. So they can operate only at one speed, which is the speed of the slowest network device on the network, and it doesn't interpret or filter the data packets. It just sends copies of each data packet to all the attached network devices on that particular hub. Okay, so again, there are various different types of hubs, but things like fast Ethernet, we've got dual speed hubs, and we've got switches. They're a type of hub, but really switches, when we get into that area, they combine the functionality of a bridge or a hub, but what switches do is they segment networks, and they can interpret and they can filter packets and the data, and send it directly to a network attached device. Switches use the network device's MAC address to really decide where that data package needs to go. So a switch operates in full duplex mode, which means that it can send and receive data to and from network devices at the same time. So typical features in today's switches, they generally offer more functionality and capabilities than the hub. So an Ethernet switch can adjust the connection speed of an inbound packet to match the connection speed of its destination network. Many switches now offer power over Ethernet, so PoE. That will enable network devices like voice over IP, phones, or other devices to get power from the switch via that RJ45 cable, really without the need of supplying a separate power supply. So other modules can be attached to the switch to enable functions like port mirroring, packet sniffers, sort of intrusion detection systems. There's really two distinct types of Ethernet switches, and they're broadly categorized as managed and unmanaged. So an unmanaged switch, the type of switch has really got no configuration capabilities at all. It's designed for small office, home office environments. Packet switching just occurs automatically on that switch, as opposed to a managed switch. So this type of switch, it'll offer the means to adjust the configuration, behavior, and operation of the switch. So access to the switch configuration is either through a command line interface, a CLI, that uses protocols such as Telnet or SSH, or even a remote console of some type via a web interface. So there are so more commonly available options to configure on a managed switch, but just keep in mind that switch manufacturers may offer different configuration options. So things like quality of service, virtual LANs or VLANs, spanning tree protocol, port mirroring, bandwidth rate limiting, MAC address filtering, SNMP clients. You can see there's lots of features that vendors are putting into their switches at the moment that offer various different networking capabilities and security requirements. Okay, and on that note then we will jump into understanding really what different types of routers are. So what have we got then? So routers, really the image there at the bottom there, they're really they link networks with a different IP range together and allow them to communicate with each other via a router. So they can interpret and filter data packets. They can forward them onto the correct network that would be configured to that router. And what they do is they use the device's IP address information to route that data package to its destination. So most routers can detect issues with data traffic that flows to any attached network and routes or reroute it around the issue. So a router is also called a gateway. When you configure network devices, you'll usually configure it with a default gateway IP address. So interconnectivity. So routers in an interconnected network maintain a routing table that lists the preferred routes between each of the networks. So the router acts as the start of authority for all of those network attached devices on its network. Routing information is shared between routers by using a routing protocol like Border Gateway Protocol, BGP. So the majority of routers use BGP for sharing information. There are some particular vendor specific routing protocols. I mean, the type of information shared depends on the usage of the router and the functions that they use. So there are several distinct classifications or types of routers available to service different network needs. So we've got access routers, typically used in small office buildings or at home. These routers tend to be low-cost devices when a simple routing method is required. We've got distribution routers. These routers compile traffic routing data from multiple routers. Distribution routers can come with more significant memory and processing power. This type of router is designed to hold vast quantities of routing information. It's often used to manage and control the quality of the service across the WAN. We've got edge routers. So an edge router operates at the boundary between your network and other networks. So for example, your local area network and the internet. They act as gateways to filter traffic and route it internally or forward it based on a packet header. An edge router often comes with access control or firewalls to improve the security. It might also handle things like DHCP and other services like DNS. So the next type of router that we can come across are core routers, so sometimes called enterprise routers. So these routers are designed for higher bandwidth. They're used to connect different buildings or geographic locations together. So core routers tend to have fewer features than edge routers because their primary focus is really on minimizing packet loss and preventing congestion in the networks. So they tend to do packet forwarding onto the edge routers. And finally, wireless router. This is a networking device that provides all sorts of routing capabilities across a regular access router, but it also offers that wireless access point functionality. So a wireless router or wireless access point is designed to provide a non-wired connection to your network. Any provision to access the internet or other networks is handled by an edge router associated with your network. So a wireless router would let you build different types of network called wireless LANs. And a wireless router shouldn't be confused with a wireless modem. So wireless modem is what you receive from your ISP to your home or your office, and it's a device that converts the signal from the ISP into one that's usable on a computer network. So wireless modems are typically combined with routers to allow you to create a private home or an office network. So let's look over to Azure then and see how that translates into Azure. So there's really two options that can help with routing and managing your network traffic in Azure. So Azure Hub and Spoke, as you can see on the diagram there. So Azure Hub and Spoke is a reference architecture. The hub is usually an Azure VNET that acts as a central connection point between the cloud and the on-prem network, and then each spoke is also an Azure VNET, and it's usually connected to the hub by a peer network, so VNet peering. So connections between the cloud and the on-prem network can be made through that VPN gateway or the Azure Express route, as I said earlier. So, and what the Express route actually is, so what that connection is a dedicated circuit between that on-prem network and the cloud that it uses generally much higher bandwidth than a regular VPN gateway connection. And an Express route circuit, like I said earlier, is hosted by a connectivity partner that really their job is there to provide super resilient sort of connections. Okay, we'll move on to some network protocols. So when you consider any move to the cloud, it's essential to know really the fundamentals of how your network's going to work, which is, I know we've covered quite a lot over the last sort of 25 minutes or so, but the first step in understanding the composition of a network is to understand how network devices communicate with each other. So this knowledge applies to your organization network and to more extensive networks like the web. So the same principles apply to all networks. So what we're going to try and look into is really understanding what's essential about network protocols that enable communication across internet-based networks. So networking protocols. So really they're sets of conditions and rules that specify how network devices communicate over a given network. So what it does, it provides a common framework for establishing and maintaining a communications channel and how to handle errors that may occur or faults that should arise across that network. So the networking protocols allow communication between different networks and network-enabled devices. So for example, between laptops and tablets and smartphones and desktops, servers and so on. So any other network-enabled device basically. Networking protocol is an essential building block in the design of an organization's network architecture. So there are many networking protocols available, but each network protocol has many properties that govern its use and its implementation. So let's look at a few of the terms before we look at some of the more commonly used networking protocols. So what is a network address? So a network address is a unique identifier that identifies a network-enabled device. A network-enabled device might have one or more of those address types, although there are more address types than this discussion that we're going to go into. So we'll focus only really on two of the main types of address types. So first one we mentioned earlier is the MAC address. So that is the burned-in address, the unique identifier that's on that device. And it really identifies that network interface at that hardware level. So the second type is the IP, the Internet Protocol address. That defines the network interface on a software level. Okay, so we'll explore these two types in a little bit more detail later on, but what is a data packet? So a data packet is a unit that's used to describe the message that two devices on a network send to each other. So a data packet consists of raw data, headers, and potentially also a trailer on that packet. The header contains several information items, so for example it includes the sender and destination device addresses. It includes the size of the packet, the protocol that was used, and the packet number, so they can be stacked up in the right order when they're received. The trailer in the data packet deals with error checking. So the concept is similar to sending someone a letter in the mail, but instead of sending several pages in one envelope, each page is really sent in a separate envelope. Enough information is sent in each envelope to allow the recipient to piece together that complete message after they've received all of the pages. So what is a datagram? So a datagram is considered the same as a data packet. So datagrams commonly refer to data packets of an unreliable service, so where delivery can't be guaranteed. Okay, so we'll move on to routing. So what is routing? So routing is, in the context of networks, refers to the mechanism used to make sure the data packets follow the correct delivery path between the sending and receiving devices on different networks. So for example, think about the PC that you're using and the server that's serving the page that you're currently watching this video on. Multiple networks might connect to your PC and server, and various paths might be available between those two devices. So that's what routing is finding that pathway through. Next, we'll look into some of the protocol categories and understand what the networking protocols are. So there's several types of applications and hardware devices depend on specific network protocols on a typical network. So for example, browsing the internet by using your web browser relies on a different protocol than sending and receiving an email, for example. So converting that data you see in the browser and sending this information over the network requires a completely different protocol. So these protocols tend to fall into three categories. So network communication protocols, network security protocols, and network management protocols. So let's have a quick look at each of these in turn. So network communication protocols, they generally focus on establishing and maintaining a connection between devices. As you work with different devices and network services, you'll make use of various network communication protocols. So first, we need to define these three foundational protocols of all of the internet-based networks. So the three protocols are Transmission Control Protocol, which is TCP. We've got Internet Protocol, which is IP, and we've got the User Datagram Protocol, which is UDP. So these protocols are concerned with the logical transmission of data over the network. So Transmission Control Protocol, TCP, it chunks up the data into data packets that can be sent securely and quickly while minimizing the chance of any data loss. So it provides a stable and reliable mechanism for the delivery of that data packet across IP-based networks. So even though TCP is an effective connection-oriented protocol, it does have overheads to help with things like error checking, error handling, and resending of packets if there is any packet loss. So Internet Protocol, IP, is responsible for the addressing of a data packet. So IP encapsulates the data packet to be delivered and adds an address header. So the address header contains information on the sender and the recipient IP address. The protocol isn't really concerned about the order in which the packets are sent or received. It also doesn't guarantee that a packet will be delivered, only the address. So finally, a UDP, a User Datagram Protocol. So it's a connectionless protocol that offers low latency and loss-tolerant implementation. So UDP is used with processes that don't need to verify that the recipient device received a datagram. So the rest of the protocols that we'll discuss here are based on any type of application. So for example, an email client or a web browser. So the most commonly used network communication protocols are things, like hypertext transfer protocol, so HTTP, how you browse the web. We've got things like file transfer protocol, FTP, is used for sending and receiving files. A really old mail protocol is POP3, so Post Office Protocol 3, not really used too much these days. The transmission of mail, SMTP, you may have heard of some of these terms. And then an older mail protocol, which was IMAP, so Interactive Mail Access Protocol. Those protocols really have been kind of deprecated. They're still around, but they're certainly not as widely used. Okay, so next we'll quickly move on to the network security protocols. So network security protocols, they're really designed to maintain the security and network of data across the network. So the protocols encrypt in transmission messages between users, services and applications. The networking security protocols use encryption and cryptographic principles to really secure any messages that are sent. So to implement a secure network, you must match the right security protocols for your needs. So the following couple of items here that I'm going to talk about, they really explore the leading network security protocols. So things like Secure Sockets Layer SSL, so it's a standard encryption security protocol. So it provides a secure and encrypted connection between your computer and the target server or device that you're accessing over the internet. Transport Layer Security, or TLS, it's really can be viewed as a successor to SSL. It provides a bit more of a stronger and more robust security encryption protocol. It's based on the IETF standard, and it's designed to stop message forgery and tampering and eavesdropping. It's typically used to protect web browser communications, email, voice over IP, and instant messaging. So while TLS is used now, the replacement security protocol is often still called SSL. So on that note then, Hypertext Transfer Protocol Secure, so HTTPS, which you may be familiar with as you're browsing the internet. You'll see HTTPS before a lot of websites. So it provides a more secure version of the standard HTTP protocol. It uses TLS or SSL encryption standards. The combination of those standards and that protocol ensures that all data transmitted between the server and the web browser is really encrypted and secure from any kind of eavesdropping or data packet sniffing. So the same principle applies to all the other protocols, so to POP, to SMTP, IMAP, FTP. So really, protocols listed previously to create secure versions known as POP-S, SMTP-S and IMAP-S, they all use those kind of TLS and SSL standards to encrypt that traffic and provide that security. Secure Shell, so SSH. So again, SSH, it's a cryptographic network security protocol that what it does, it provides secure data connection across a network. So SSH is really designed to support command line execution of instructions which might involve remote authentication to servers. For example, FTP uses many sort of SSH functions. Accessing Linux or Windows servers or any kind of server really can generally be accomplished using some kind of an SSH functionality. Okay, Kerberos. So Kerberos is really, it's a validation protocol. It really provides a robust authentication for client-server-based applications through a secret key cryptography. So Kerberos assumes that all endpoints in the network are insecure by default. It enforces strong encryption for all communications and data at all times. Okay, so network management protocols. So in your network, it's perfectly acceptable to have multiple different protocols running concurrently. So previously we discussed communications and security protocols, equally important to the successful day-to-day running and operation of a network. So they are really the management protocols. So the focus of this type of protocol is the sustainability of the network by looking at faults and performance. So network administrators need to monitor their networks and any devices attached to them. So each device in your network exposes some indicators about the state and health of that particular device. So these indicators are requested by the network administrator toolsets, and they can be used for monitoring and reporting. So there's a couple of different network management protocols, but we'll quickly run through those. So the first one being, so it's called the Simple Network Management Protocol, so SNMP. So it's an internet protocol that allows for the collection of data from devices on your network and the management of those devices. So the device has to support SNMP to gather information. So devices that typically support SNMP include switches, routers, servers, laptops, that kind of stuff. Printers maybe. The second management protocol can be viewed as the ICMP, so Internet Control Message Protocol. ICMP is one of the protocols included within the Internet Protocol Suite. It allows network-connected devices to send warning and error messages along with operational information about the success or failure of a connection request, or if a service is unavailable, Unlike other network transport protocols like UDP and TCP, ICMP isn't used to send or receive any data from those devices on the network. We'll talk briefly about ports now. So a port is a logical construct that allows routing of incoming messages to a specific process. There's a particular port for every type of IPS. So a port is an unsigned 16-bit number from the range of 0 to 65535, and it's also known as a port number. So ports are assigned by the sending of TCP or UDP layer based on the communications protocol use. So there are specific port numbers reserved for every service. The first 1024 ports, called the well-known port numbers, are reserved for the commonly used services. So the high number ports, called the ephemeral ports, are unreserved and used by dedicated applications. So every port links to a specific service or communications protocol. It means that the target network device, say a server, can receive multiple requests on each port and service each of them without conflict. So well-known port numbers. So much in the same way that IP addresses are split into classes, so are ports. There are three ranges of ports: well-known ports, the registered ports, and the dynamic and private ports. So the Internet Assigned Numbers Authority, the IANA, they manage the allocation of port numbers. So the regional assignment of IP addresses and the domain name system root zones. So IANA also manages a central repository for protocol names and the registry used in Internet Protocol. So on the screen there we can see some typical port numbers. So port 80 is HTTP, port 443 is HTTPS. Okay, so we'll look at the Internet Protocol Suite. So the Internet Protocol Suite is a collection of communication protocols, also called a protocol stack. So it's also sometimes referred to as TCP/IP protocol suite, since both TCP and IP are primarily protocols used in the suite. The IPS is an abstract layered networking reference model. So the IPS describes the different layered protocols used to send and receive data on the internet and similar networks. The IPS model is one of several similar network operating models that varies between 3 and 7 layers. The best known model is the Open Systems Interconnection, so the OSI model, networking referencing model. So we're not going to cover the OSI model here. I'll put a link up in the description below to learn, as a learn more item. But really, we'll look at some of the common layers within that model that are used. So application layer is the top layer of the stack that's concerned really with applications or process communication. The application layer is responsible for determining in which communication protocols are to be used, on what type of messages to be transmitted. So for example, the layer assigns the correct email protocol such as POP SMTP, and the message is email in its content. So the transport layer, this layer is really responsible for host-to-host communication on the network. So the protocols associated with this layering, they are TCP and UDP. TCP is used for flow control, UDP is responsible for providing a datagram service. The internet layer, this layer is responsible for exchanging datagrams. So a datagram associated at this layer it'll contain the data from the transport layer and adds in the origin and the recipient IP addresses. So the protocol associated with this layer are IP, ICMP, and Internet Protocol Security, so IPsec suite. And then finally the network access layer. So there's a bottom layer of the stack, and it's really responsible for defining how the data is sent across the network, and the protocols kind of commonly associated with this layer are ARP, MAC, Ethernet, DSL, and things like ISDN. Okay, so monitoring networks in Azure. How do we manage and maintain networks once we've got them set up and configured in Azure? So that management of the health and the monitoring of your network is the same across all networks, really, no matter where the location of that network is. So for example, a local organization's network uses the same network standards and protocols as an Azure based network. So Azure has got 3 network monitoring tools to assist you with maintaining and managing the health of your networks. So you can also extend some of those monitoring features to on-prem networks as well. So first, we've got the Azure Network Watcher. So you can use the Network Watcher to capture packet data from the Azure services that you use. You can understand the flow of that data and network traffic patterns, and you can use it to troubleshoot network-related problems across your network. The next tool is the Network Performance Monitor. So the Network Performance Monitor, it monitors and it reports the health of your network. It provides insights into your network's performance, and it can also report on the connectivity between any applications that you've got configured across that network. So whilst the Network Performance Monitor is cloud-based, it can actually provide a hybrid service on to monitor some of your on-premise network infrastructure. And the third tool is the Performance Monitor. So Performance Monitor is a capability within the Network Performance Monitor, and it's really designed to monitor network connectivity across your entire estate. So whether it's on-prem, it's cloud-based, it reports network issues as they occur. You know, Performance Monitor, it can monitor all types of routes along with its redundant paths, and it can report on any kinds of issues. It can identify particular network segments that degraded with degraded network performance. It can also report on the health of the network without needing to rely on any management protocols like SNMP, for example. Okay, so IP address standards and services. Okay, so when you're considering that move to the cloud, it's really essential in your role as an Azure developer or a solution architect to know how your network is actually working. So really speaking is you know, we've talked a lot around sort of internet protocol, transmission control protocol, the internet standards, and the way that networks are kind of hung together. One more point around protocols, really. These protocols are related to IP address standards. So we're going to look at 2 main ones in particular. So the first one being the Address Resolution Protocol, so ARP for short. So this is a communications protocol within the IP suite, and it's a request response protocol used to resolve any MAC address for any given IP address. So ARP supports many data link layer technologies, so such as Internet Protocol version 4, IPv4, VNET and POP. So when an IP version 6, IPv6 is resolved, the neighbor discovery protocol, NDP, is used instead of ARP. So ARP is really for IPv4, NDP is used with IPv6. So without ARP, there would be no means to resolve an IP address to that physical MAC address. So essentially, ARP is like the DNS of MAC to IP. There's also reverse address resolution protocol, so RARP, which retrieves IP addresses based on a given MAC address. So the second protocol we're going to look at is the TCP/IP, so the Transmission Control / IP Internet Protocol. It's a collection of different communications protocols, and they support and define how network-enabled devices interconnect with each other over an IP-based network. So at its heart, there's 2 key protocols, TCP and IP, and it makes the internet possible, as well as private and public networks like intranets and extranets. So TCP/IP defines the way data is shared between network-enabled devices by defining the end-to-end communications process. Yeah, it manages how the message is broken down into packets of data, which are sometimes known as datagrams. So we've discussed this earlier on. It also determines how the packet is addressed and transmitted and routed and received. Okay, so TCP has got a couple of different model layers. We'll touch on them briefly, but it's made up of 4 distinct layers. So each layer has got a different type of protocol. So notice how the TCP/IP model is similar to the IP model suite discussed earlier on. So we've got the application layer, we've got the transport layer, we've got the internet layer, and we've got the network address layer. So as we discussed earlier on, they've got a very similar structure. Okay. So Internet Protocol standards. So remember earlier on that we were talking about IP. it's not really concerned about the order in which packets are sent or received, and it doesn't even guarantee that that packet will be delivered. So the IP, the Internet Protocol, only provides a logical addressing scheme that's used to route and forward messages to their destination. So today we use two Internet Protocol versions that work within the network. So IPv4, released in 1983, it was a standard for all packet switch networks used today. IPv4 uses 32-bit address space, and it gives an upper limit of 4.3 billion unique logical IP addresses, roughly, just under. A large number of these available IP addresses are reserved for specific purpose. So, for example, private networks, local hosts, internet relays, documentation, and subnets. So, the structure of an IP address is 4 decimal numbers in the range of 0 to 255. So, each of those is separated with a dot. So, it's also known as dot decimal format. So, an example of an IP address, as you can see there, might be something like 192.168.10.10. So each part of the IP address, there's fundamentally two parts. There's the network and the host. So let's use the address of 192.168.10.10 as the example. So the network part of the IP address covers the first set of decimal numbers. So in this example, it would be the 192.168.10. This is unique to the network and specifies the class of the network. Okay, there are a number of network classes available, which we'll discuss shortly, but the host part of the IP address covers the next set of decimal numbers. So in this example, it's 10. So this number represents the device and it has to be unique within that network to avoid any kind of address conflicts. So IPv4 address classes. So Internet Protocol's local address space is split into 5 logical classes or ranges of IP addresses, each represented by a letter of the alphabet. So for classes A, B, and C, the start and end of the IP addresses are reserved and shouldn't be used. So class D is reserved for multicast traffic only. Class E is reserved and can't be used on public networks like the internet. So in the previous table, the last column is marked as a subnet mask. So the subnet mask really uses the same format of the IP address, but its purpose is to identify valid IP addresses in that IP range. So for example, assume you've got an IP address range that starts 192.168.0.1, and you've got a subnet mask of 255.255.255.0. You'll apply the subnet mask in the following way. So for each address segment's value, the specified as 255 in the mask, the corresponding address segment is static. So when you want to pick an IP address, you have to pick an address that matches 192.168.0. Yeah, so that's what those 255.255.255. It means that it has to start with those 3 octets. So where the segment has got a value of 0 in the subnet mask, you're allowed to use any value between 0 and 255. So a subnet mask of 255.255.255.0 gives an IP range of 192.168.0.0 to 192.168.0.255. So all of that range are valid for a particular network device to select and use. Okay, so what is a subnet? So really a subnet is defined as one or more logical networks within the classes A, B or C networks. So without subnets, you're restricted to a single network in each of the class A, B or C networks. So an IP address, also known as a network address for root or routing prefix, represents the address of the device or computer that's to send the packet of data to. So a subnet or host address represents which network or subnet network to use. A subnet is a 32-bit number framed using the dotted decimal format. So as we just discussed, that subnet mask could be 255.255.255.0, and that is a standard subnet mask. In an IPv4 network, for a packet of data to be routed to the correct network and the right network device, a routing prefix is needed. So a routing prefix is created by taking the subnet mask and applying a bitwise AND to the IP address. So a more common way to define the subnet and the routing prefix is to use the classless interdomain routing notation, so the CIDR notation. So that applies to IP addresses as the number of bits you want to allocate to your subnet. So using CIDR notation, at the end of the IP address, add a / and then the number of bits. So for example, 198.51.100.0/24 is exactly the same as using the dotted decimal format subnet mask of 255.255.255.0. It offers a range exactly like we discussed earlier, 198.51.100.0 to 198.51.100.255. So sublets allow multiple networks to exist within one network, and they can be enhanced routing performance, and subnets can be arranged hierarchically to create routing trees. So special use addresses. Each of the classes has got restrictions on the ranges of IP addresses that can be used. So this table on the screen here, this shows some of the more common ones. So IPv4 address space exhaustion is going to happen. So soon after the introduction of IPv4, it became apparent that the pool of available IPs was being consumed far faster than was ever expected. So for example, think about the number of mobile devices that have been released in the last couple of years. Several solutions were introduced to mitigate the threat of running out of IP addresses. So these included network address translation, NAT, classful networks, and CIDR. So in the 1990s, IPv6 was created to increase the number of IP address spaces to 128 bits. So IPv6 was introduced commercially in 2006. Private IP addressing. So in classes A, B, and C, a range of IP addresses are set aside for private networks. So these IP addresses aren't accessible via the internet. All public routers ignore any packets sent to them containing such addresses. So network devices on a private network can't communicate with devices on a public network. Communication can only happen through network address translation at a routing gateway. So the only way to connect two private networks in different geographical areas is to use virtual private networks, VPNs, and a VPN encapsulates each private network packet, and then the VPN can further encrypt that packet before it sends it across the public network for one private network, or from one private network to the other network. IPv6, as I mentioned, so IPv6, it's the latest version of the IP standard, and it was designed and developed by the IETF to address the problem of IPv4 logical address exhaustion, and to eventually it'll replace the standard. It was adopted and recognised as an internet standard in July in 2017. It uses 128-bit address space, which allows 2 to the power of 128 addresses. So yeah, the amount is approximately 7.9 times 10 to the power of 28. So time it's huge. IPv4 and IPv6 they weren't designed really to be interoperable, which has slowed down that transition from IPv4 over to IPv6. So IPv6 has also introduced some new benefits, so things like simplified network configurations. So IPv6 has got address auto configuration built into the protocol. So for example, a router broadcasts the network prefix, and the network device can append its MAC address to self-assign itself a unique IPv6 address. Security, IPsec is built into IPv6. New service support, so IPv6 eliminates the need for NAT, which makes it easier to create peer-to-peer networks. Multicast and anycast functionality. Multicast allows for the broadcast of messages in a one-to-many fashion. Anycast allows for single destination to have multiple routing paths to 2 or more endpoint destinations. The structure of an IPv6 address, it is vastly different from an IPv4. So instead of those 4 decimal numbers, it uses 8 groups of 4 hexadecimal numbers called hexadectet. So each hexadectet is separated with a colon, and a full IPv6 looks like you can see there on the screen. Really, it's quite a long number. So So the new standard, what it allows for, the addresses, they can be simplified by using sort of the following rules. So any leading zeros to any group can be removed. So if, for example, you were typing 0042, well, that can just be written down as 42 instead of having those leading zeros. So consecutive sections of leading zeros can be replaced by a double colon. So rather than having multiple 0000s, you can just put colon, 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 which shortens the version of that IPv6 and allows you to remove any mention of zeros. DNS. So the domain name system is a decentralized lookup service that translates human-readable domain name or URLs into IP addresses so that the server that's hosting that site or services can be contacted. The worldwide distributed nature of DNS is a vital component of the internet. So DNS has been used since its inception back in 1985. So a DNS server is really used for two purposes. First is to maintain a cache of recently searched for domain names, which improves performance and reduces network traffic. And the second is to act as the start of authority for all the domains under it. So when a DNS server is looking to resolve a domain name that isn't held in its cache, it starts with the highest level, the dot, and then it works down with the subdomains until it finds that DNS server acting as the start of authority. So once it's found that, it stores the IP address of the domain in its local cache. DNS also holds specific records that relate to a domain. So these records, much like the start of authority, but it can also include IP addressing in the form of A or quadruple A formats. So SMTP can be held in DNS in terms of mail exchanger records, MX records, and then domain name services can be held in DNS as name server records, NS records. And finally, there's an alias functionality called a CNAME. So rather than something relating to a change to an IP, you can translate a host to another host by using a CNAME record. So what do we get in Azure? So while many of the concepts discussed here are technical, so Azure builds and extends several of these aspects with tools that can help configure the network. So we've already discussed networks, the VNET, VPN gateways, and express routes. What else have we got? So really at a high level, we've got Azure DNS. So it's a service for hosting registered domain names by using the Azure infrastructure. So you can create an Azure DNS to manage your DNS records, such as those mentioned, quadruple A, CNAME, NS, MX records, and you can sign in using your regular Azure signing credentials. So Azure DNS won't replace domain registrars. So where you register and purchase domains, Azure doesn't do that at the moment. So one of the core benefits provided by Azure DNS is the alias record, which can use either an A or quadruple A or a CNAME record. So by using the alias, for example, you can route traffic to an Azure resource. And then secondly, the Azure VNET. So we discussed this earlier on. So you can use the Azure Virtual Network to build a private network in the cloud. So with an Azure Virtual Network, you can build networks that can communicate with other virtual networks and your on-premise network. So they're an efficient way to extend your network into the cloud. With an Azure Virtual Network, you can control the addressing that's used, and most virtual networks are assumed to be private networks. As with regular networks, you can use subnetting and segments to segmentate and give unique IP address ranges to those subnets. And on that note, I think we're done. Thank you for watching my video. It's been a little bit of a journey. Really appreciate you sticking around to watch the remainder of the video. We really appreciate it if you could like and subscribe to my YouTube channel. Like I say, that was my first video. It's been over an hour. We're talking about some really interesting stuff and deep level stuff in Azure Network. So hopefully some of that information was good to you, for you to use. Like I say, really appreciate you sticking around. Give me a subscribe, give me a like, say hello. As I say, it's my first video, so please give me some feedback. Let me know what worked, what didn't work. I'm obviously going to watch this back myself now and have a little look and see how we're getting on. But on that note, really appreciate it. Thanks for sticking around. Hope to see you at the next one.